can record it.
Question number 17.
Okay.
That is, let f such that R be an infinitely differentiable function.
Okay.
Such that for all AV belongs to R with A less than B.
Strictly.
Yeah.
Hmm.
Then also given that f of B minus f of A by B minus A
Hmm.
by B minus A
Hmm.
equals to f dash A plus B by 2.
Yeah.
Then now there is given some options. You have to find out which one is correct and not.
So this is like a quadratic, right? No?
What that means?
Is f not a quadratic polynomial?
I don't know how
Okay.
to find this out.
Right. Let's see what they're asking that the options will tell. Okay. Okay. So what are
Should I tell?
yes.
Okay, the options are f must be polynomial of degree less than or equal to 2.
Uh and
Second one is greater than 2.
uh
F is not a polynomial.
uh
F must be a linear polynomial.
okay. So it's all questions around polynomials, right? Okay.
Huh.
Yes, as I was saying that this should be like a quadratic polynomial. Right? Let's try to see. So certainly, if f is linear, then this is true, right? So, is that fine with everyone? I mean, if it's not, then just say. And what about quadratic? Is this true for quadratics? Yeah, you can just, Arika, if you have something to say, you can just say.
Sir, what is the notation? F belongs to C to the power infinity bracket R. What is the notation?
This is just infinitely differentiable. Okay.
And what is C?
Yeah, so you can just translate it to infinitely differentiable. Okay, and you have to, yeah, later you can check this out. Okay, why this C is there? It's there is a reason, but yeah, C is for continuity, but just you can assume that it means infinitely differentiable. It doesn't help. This notation doesn't help. I just wrote it. I write it like that. So linear polynomials work certainly because slope is constant. But I just said that quadratic should work. And can you just check if quadratic works? Take a quadratic and check it.
For fx equal to x square, it is, I mean, right. Matlab,
It
this
works.
property is holding.
Yeah.
Yeah,
So just check it
but
for
I
any.
don't know.
And just check it. No, write x square because c and check it. And then we will prove that degree of fx, and then it will prove that it's a polynomial.
Sir, is F is a polynomial?
It's not given, but if you can prove that, then that will be good. But it is true. You can prove it, I think. So it's not given, but it is true. That is the main question. If you can prove it's a polynomial, then you are done. So someone should just check and tell if every quadratic works. Fx.
Shouldn't it work something?
It works for every quadratic, right?
Yeah.
Yes. Correct. So this is what I said in the beginning, that this should be quadratic, but I'm not able to find a reason now to say, a nice reason to say. But of course, you can just check it, write it, and check it that it works. But what should be a nice way to say that? because f dashed is a linear function. Yeah, like I mean, I can see a reason, but it's okay if you see it like that also, it's fine. So the reason is to rotate it, right? Because you know that if you take A and B to be such that FB is equal to FA, then you know that it's right at A plus B by 2 where the slope is 0, right? Because the maximum is attained at alpha plus beta by 2, right? Maximum or minimum. So that, and then if you rotate, then things are just same, and geometrically it remains the same. Yeah. So now the goal is to show f is a polynomial. So this should be the first step, and then you show that f is a quadratic. Means it cannot be degree 3 or something. That I mean, if it's a polynomial, then certainly it has to be a degree 2, because if it's a polynomial, then you already have this expression that a plus b by 2 times no a x plus a by 2. Okay, that's not what I wanted. Just a minute. So if we assume 1 for the moment, then why is it? So it's x plus h, and I mean, so you can just show this directly, okay? So this you can show directly. You just assume that it has a polynomial expression, right? And then you can work on that, right? So this thing would be something like a n b to the power n minus a to the power n, and yeah, so on. And then by b minus a. Yeah. No, but there should be a better way, right? So from here you can, yeah, from here you can certainly do it. You can compare coefficients and so on and show that n is at most 2. But there should be a better way. So let's think about that. I mean, geometrically, what happens is that if it's higher degree, then there would always be a asymmetry. So x minus 0, x times f dashed of x by 2, right? You can also use this. See if this gives a better solution to thing. Yes, right? Because you'll have these powers of 2 and everything, right? So that should tell you. So it is n, right? So when you compare the coefficient, you will get that n should be 2, right? Because it's x. Calculating is a bit of trouble. This, and then you compare the coefficients. Okay, there was also an an, so that we can just assume is not there anymore. And then from here you see that this has to be 1, and so you know what n has to be. Okay, n has to be 2. So all that is fine. So our 2 implies, so 1 implies 2 is fine. So as I said, that the focus should be to prove that it's a polynomial, because that seems to be the right. So now we should try to show that it's a polynomial. But yeah, this is not a good good like. But as you can understand, right? I mean, this is what is saying that if there is a horizontal chord, right? If there is a horizontal chord and this, okay, and then the slope is 0 of the chord, then this is also saying that the midpoint that at a plus b by 2, if a and b, if f of a is equal to f of b, then f of a plus b by 2 is a slope 0. That kind of thing means a symmetry, and that only happens when you have a quadratic. Yeah, means you can prove that actually rigorously. But yeah, so but anyways, we have taken care of that. We show that f is a polynomial. How do you prove that something is a polynomial? Because f is only c infinity, so it's only infinitely differentiable. It's not given that it has a power series. Then maybe you could do something. How do you show something as a polynomial? So just think of this as a functional equation, right? And try to use your tricks of functional equations. Show that it's a polynomial. Yeah, so I mean, the idea should be that I think is better to prove both directly. That you try to show that the higher derivative at one point the derivative is zero. That should be the way, right? Show that at one point the derivative is zero. So think of these as a, and obviously they are variables. So, okay. So what can you do? I'll just use the same thing again. So the idea should be to show that the higher derivatives are zero. And you can just assume f of 0 is 0. That's not going to change anything. Just translate the function. All these facts are going to remain the same. So I'll just assume this is 0. So you don't have to think. Because you can just translate, and if this fact, this equation will still be true. Is this useful? This equation? Can we do something? Yeah, this maybe is a little tricky, but yeah, maybe you can take like some x and minus x, right? Just to use the equation certain way, right? So this will be oh okay, 2x times f dashed 0. So this is there also for every x. So this is constant, right? So we get that this, and I think what I did is not so good, because you can do this anyhow you want, right? No, like what you do is you take x plus some constant, and you take this to be x, and the constant is fixed. then again by the same trick, you get that f double dashed x plus c is equal to f double dashed x. Is that correct? For all x and for all c, right? And this just solves the problem, right? It just finishes the problem, because now you know that f double dashed is a constant function, so f triple dashed is 0, and then everything follows. You integrate and so on. Is it fine?
Can you explain it once again? I did not get this.
Which part?
Uh, the last if double dash or if
Yeah. So if you see this one, you agree that f double dashed is equal to this, right? F double dashed minus x. But you can just do the same thing with anything else, right? X plus c also, right? So
yes,
we-
yes.
yeah, let's just check. Maybe there's something. Yeah, you can do it. You just take this and yeah, I mean, you can do it, I think, better than me. And just, yeah, okay. It just comes. Yeah. So this, I mean, the problem is very simple. One has to figure out, like, one has to know what is. I mean, you think about it, right? But I am sure that this is not a this condition infinitely differentiable is not needed. Okay, there is some deep results. I cannot prove them, I think, but I can. But I can check it and share it with you, and you can see. But this solution is fine. I mean, you should think. I am not going to give you motivation and so on. You should think on your own, and then you can find the motivation. Okay, but yeah, let's, because so this is like the Lagrange mean value theorem, right? But it's happening in a very special way, and that itself is implying that uh, that the function is polynomial. And I don't think you need to assume. Let's see what happens. I mean, all these things, of course, you do after you have tried and tried the problem for hard enough. We have done it, so now we just want to judiciously use the internet and see out something. It's a very nice theorem. I mean, it's a very nice thing is that when the Lagrange mean value theorem always happens at the midpoint, then the thing suddenly becomes a polynomial. And I don't think we. You may share solution now. I don't know. I've shared the solution. Yeah. Okay. Oh, yeah. That's what I meant. I mean, so what I'm saying is that, like, if you just assume that f is singly differentiable, then also you are done, right? Because the multi-differentiability automatically comes, right? Because you just differentiate it, and then the second derivative will exist because it's equal to the first derivative. I think, right? You automatically get that f is infinitely differentiable. Yeah, so that's why it felt to me it's not needed, but it's already present on the notes. Okay. Yeah. So then I don't think I can say anything really, because I cannot say anything, because then it's really already, yeah. I mean, that much we need that test is. Yeah. Any comments on this? Okay. So it's important to know that it's going to be a quadratic. That's important. Maybe if you see this from Taylor's theorem angle, then also maybe you can get it fast. So Taylor's, because you can use the infinite differentiability. I don't know. That's what I thought first. So this is your Taylor's theorem, right? And then we just need some, please help me with the Taylor's theorem statement. No? No, this is fine, right? It is h to the power n plus 1 by n plus 1 factorial, and this could be n plus 1 derivative, but at some c which you cannot control. It's between c is between, right, x and x plus 1. Is this correct? Is this version correct? There are many versions of this. So this is Taylor's theorem. And now what you are given, you can compare it with this and maybe you get something, right? You just take h equal to, I'm doing something wrong. No, you just take x equal to 0. And yeah, you see what I'm trying to say, right? If you stare at this for long, you will automatically see that this tells you that the higher derivatives are 0. That problem, that given condition, right? Do you feel that? Is that correct? If you compare it with that, kind of happens for every x, you can maneuver all that, and you see that it is Taylor's theorem, just the statement of Taylor's theorem and that statement, if you combine them, you see that the higher derivatives are forced to be 0, which also solves. So you don't have to do any calculations. That's done in the proof of Taylor's theorem. So once and for all. And so, yeah, I think that's maybe one another thing. But really, I would just say that the symmetry thing is really okay. So before this meeting is going to end in a minute, so I'll just share this means for you one place to see these geometric things quickly. There is a book called, I just write it here and you can just, and then it's up to you. There is a book, I think I've referred to this for other things earlier, More Calculus, and it's really a high school book, okay? It's really like high school means it's just a calculus book. More calculus within one variable. So here you will see that there are some chapters on mean value theorem. So they really tell you all these geometric reasons. Okay, there is a chapter on mean value theorem, some chapter number. You can check this, and there is called Mercer is the author's name. Okay. So anyways, now the meeting is going to end. So we will take some 7-8 minutes break and then we'll join because Zoom will restart after some time. Okay, is that fine? So please join back and see if you have questions.